Okay, the first problem I'm going to work for you is problem number 2. And where did I put the extra copies? So first of all, let me draw your attention to the header. So I asked ChatGPT to generate 10 real-world contexts for me with realistic problems. And this is what they came up with. Whether these are realistic or not, we will see as we go through. So as we go through and see these results, let's ask ourselves the question, do these results seem realistic? Or did ChatGPT just throw some junk and these results aren't realistic? So we'll see. I did ask it to keep the equation simple, so it probably might have kind of fudged things a little bit. But let's look at this first one. This is the second one, car acceleration. I've got the distance is measured in what units? M, and M normally represents meters. So distance is measured in meters here. What's the variable, when you look down to the equation, what's the variable they're using to represent distance? Look at that equation. T is used for something, but T is the time. So T is the time measured in what? Hours. What does it say there? It says seconds. And the function uses S for distance and kind of that condensed function notation. So they've given us this. S of t is equal to 4t squared plus 10. So this is what we're given, that the distance traveled in meters as a function of seconds is given by this, where we take whatever the seconds is, square it, multiply it by 4, and then add 10. That tells us the total distance traveled in that number of seconds. Are you with me on that? Okay. So now let's start to dive into what we're asked to do. The first thing we're asked to do is find the average speed from t equal 2 to t equal 4. So how do we do that? So average speed from t equal 2 to t equal 4. And Luke, I think you have some ideas.
You plug in 2 and 4.
Okay. So what's S of 2 equal to?
26.
You agree that's 26? 26 what? Meters, right? Because S is measured in meters. This is 26 meters. All right, let's do S of 4. S of 4 is 4 times 4 squared plus 10, which is going to equal how much?
74.
74. 74 what? Meters. So I've got those two values. I need to figure out the average speed. What do I need to look at? The change in distance over the change in time. So what does this become up here in the numerator?
74 minus 26.
74 minus 26 all over 2. And let's go and keep going. 74 minus 26 is how much? 48. 48 over 2 is how much? 24 what? What are these measured in? Meters per second. Luke, you spit that out really fast. How did you know that?
Because the input on the top was meters and the bottom was seconds.
We knew all along these were meters up here. We knew down here these were seconds. So 24 meters per second. So we've determined that between seconds 2 and 4, our distance was changing at an average rate of 24 meters per second. Does that mean it was changing that much every single second? No, it just means that if it were going at a constant change, it would be 24 meters per second. But we know it was variable, but on average, it turned out to be the 24 meters per second. Okay. Are we good on that so far? Okay. So now let's continue on. What's the next thing we're asked to do?
Instantaneous speed at t equals 2.
So now we need instantaneous speed at t equal 2. So how do I figure that out? Nice and loud, Carson. We need s prime of 2. Let me get s prime of t first, and then we'll get what s prime of 2 is. Looking over here at your equation, what is the derivative of this equation? 8t, right? So the derivative of the 10 is what? 0. Then the derivative of this is 8t. So s prime of t is 8t. What are the units on that, by the way? It's still going to be meters per second, right? Because remember, when we're doing the derivative, it's changing output over changing input. So it'll still be meters per second. When I evaluate this function here at 2, what do you guys get? So 16 meters per second. So right in that moment, right at 2, the instantaneous rate of change was 16 meters per second. The average was 24, but right there at 2, it's 16 meters per second. Okay, good. So we found the instantaneous rate of change there. Then what are we asked to do?
Position at 2.1.
Predict at 2.1 seconds. So the idea of what we're going to do, we've just figured out what the slope is of this line. And we're going to go out just a little bit and predict the function value using a tangent line. Okay, we're just going to go out for the line. So I'm going to find the equation of the tangent line first, and then I'll use it. So the equation of the tangent line. So that equation of the tangent line is going to be y minus. Now this line goes through this point AF of A, or in our case, it goes through the point 2, 26, right? So here's y minus 26, there's the y value, is our slope. What was our slope? 16 times x minus the x value over there, which was what? 2? All right, how many of you just got lost right here as soon as I did this? Okay, so let me do a quick refresher for you. There's many different ways to write lines. The one you're probably most familiar with is this one. Y equals mx plus b. Are you most familiar with that one? Here's another way to write lines. Y minus y1 equals m times x minus x1, where x1, y1 is a point on the line. Anyone know what this form is called? This is called point slope. For this problem, what do I have? What do I know right off the bat? What do I have? I have a, what is this? It's a slope. What is this? A point. I have a point and I have a slope. So using point slope is going to be the easiest way for me to get there. So that's what I did. I just plugged in my point, 226, plugged in my slope. I've got an equation. Now, if you want to go down and go from here to here, you absolutely can. And we'll go ahead and do that. So I'm going to move the 26 to the other side. Let's go ahead and distribute the 16. I get 16x minus 32 plus the 26. That ends up being 16x minus 6. So this is the tangent line. So that's the equation of this line right here. And I can use that line to predict my distance at any point in time. The further away I go from 2, it's going to become less and less accurate. Now, what questions do you have on this so far? Yep.
So that equation that you just got, so it says like predict position at 2.1. Would you just plug 2.1 in for x then?
Yep, that's exactly what we're going to do.
Okay.
So predict when t equals 2.1. So now we're going to go down here. The y value we're looking at is 16 times 2.1 minus 6. And someone do that. What do we get? 32 point. No, sorry. Yeah, it's 32.16 minus 6. Is that what you guys got? Am I doing that? I'm trying to do it in my head, but I might be doing it wrong. 32.
27.6.
No, 27 point. All together, right? After you did the minus 6. So it was 32.6.
33.6.
33.6 minus the 6, and then that simplified to 27.6. What are the units on this? What are we predicting here? Are we predicting a speed?
Meters away from the stars.
This is the distance. This is back to distance, and these are what? Meters. These are just meters. Okay. So we've predicted that 2.1 seconds into the journey, if you will, the distance traveled will have been 27.6 meters. So this is our estimate. It's our tangent line prediction. Estimate. Let's see how close we were. We could evaluate our original function right here at that 2.1. Let's just do it now. S of 2.1. Someone's going to have to do that. I can't do that one in my head. 0.1 squared plus 10. What do you get?
It's like 27.64.
27.64 is the exact answer. Our decimal approximation was 27.6. How close were we? Pretty close. Which was easier to compute? I guess you got calculators nowadays that doesn't
Probably
matter.
the second one.
You think this one is easier to compute?
It faces one thing, yeah.
Yeah. I mean, this is more complex, but with calculators, it really doesn't make a difference. But historically, you would go for the easier one. It's easier to compute. Okay. So that's a pretty good estimate. So that's what we're going to be practicing is estimating function values. And the reason we need this is we don't always know the equation of the function itself. We might be using numerical methods to determine the instantaneous rate of change, the function value. So sometimes we're predicting when we don't even really know the parent function, the original function. And so that's why you can use these tangent line approximations. All right,